We can now look at things like locus in a different way. Now that we think of a complex number as a vector. So let's go back to circles. We mentioned it briefly earlier. There's our standard circle centre at the origin. Now we said before we could write this as z times z conjugate, because of course that is x squared plus y squared, which is the modulus squared. So another way of writing, if z times z conjugate is r squared and z times z conjugate is modulus squared, well then I could just simply say the modulus is equal to r. Now that makes sense. Because if I get any point on the circumference here and join it up to the origin, the length of that vector would be the radius of the circle. So modulus of z equal to a constant number, got to be a circle. And if we shift the centre to some other complex number then, now we say, well, before we said, z minus omega, conjugate of z minus conjugate omega, very clumsy. There's a much neater way of doing that now, because all we're saying is, well, if I join any point up to omega, the length of that vector will be the radius of the circle. So modulus of z minus w, which means the length of a line is a constant amount, and omega is constant, it's not moving, z's the thing that's moving, it must map out a circle. And it sticks with the idea of point on the circumference minus the centre, which is what we're used to with circles. So hopefully we see those sorts of things, we recognise them straight away, and we know, okay, that's going to be a circle. So let's have a look at these circles. Well, x squared plus y squared equals 16. There it is in Cartesian form. So we now can simply say, oh, well, that's it. On the Argand diagram, it's the modulus of z is equal to 4. Because we've got a circle, centre naught, radius 4. If we wrote it the other way with conjugates, then it would be z conjugate is 16. The thing to be careful with the alternative format is it's radius squared, not radius. Let's move the centre. Okay, as that stands, it's a bit hard to work out where the centre is. So let's complete the square. And eventually, there it is. So x plus 3 squared, y minus 2 squared is 25. So we're joining z up to the complex number negative 3 plus 2y, but it's minus the centre. So it actually matches the numbers that are in the parentheses there. Plus 3 minus 2i is equal to the radius 5. In the conjugate form, we have that beautiful looking statement, z plus 3 minus 2i, conjugate of z plus 3 plus 2i is 25. Let's go the other way. Well, find the centre and the radius. Z minus the centre. So the centre is, well, in Cartesian coordinates 5, 1, complex number 5 plus I, however we want to write that, and the radius is just 2. There it is in that messy form, but remember if we've got it z minus centre, z minus conjugate, and they are conjugates, 4 plus I, 4 minus I. So the centre must be minus 4 minus I for this one. And radius 7. Not immediately obvious. Modulus of 3 times z is equal to the modulus of z plus 2 minus I. So in other words, if we get a complex number, we join it up to the point minus 2 plus 1. The length of that vector will be the same as if we multiplied z by 3 and joined that up to the origin. What on earth could that be? I mean, again, can't really tell. So if you can't tell, let's go back. Well, I can tidy it up a bit. And I've got 3 times modulus of z. So remember, modulus is absolute value. Absolute value is just grouping symbols. So I can factorise out. And the absolute value of 3 is 3. So I've factorised that out. But I'm still not sure. So let's take it back to Cartesian, subbing in our x plus I y's. Mod z is x squared plus y squared, or square it off. But I'm also squaring both sides, you'll notice. So the 3's turn to 9. And on the other side, we get x plus 2. It's again looking like a circle, because I'm going to have, well, when I expand the right hand side out and take it to the left, I'm going to end up with 8x squared and 8y squared. So coefficient's the same, going to be a circle. So let's work it out. Move it to the left. A lot easier to complete the square when it's just 1x squared, 1y squared. So there we go. Aha! Yes, as suspected, a circle. Of course, I guess the other hint was that we're looking at circles at the moment, which kind of was the giveaway. So centre 1/4 minus 1/8, radius 3√5 on 8. Oh, one of those ones in conjugate form. Z conjugate plus 2 lots of Z plus Z conjugate. Well, hang on, Z conjugate, x squared plus y squared. Z plus Z conjugate, 2x, twice the real part, yeah. And so again, yet another circle, complete the square, and there we are, centre minus 2, 0, radius 2. Alright, so that's circles. Let's look at lines. Now, we mentioned that a horizontal line means every point on there, the imaginary part of that complex number would be the same. So you end up with a horizontal line. And vertical lines, similar, but now it's the real part is always the same. We'll get a vertical line. So they're the two most basic lines, I suppose, horizontal and vertical. But what if it's at an angle? How would that look? Okay. The way we can describe this line is the perpendicular bisector of 2 points. We can find 2 points, and there are probably lots of different points we could use that would give the same line. But I guess what I'm getting at is if I see modulus of a linear function, so z minus something, equals modulus of a linear function, then I know we're talking a line. Because what we're saying is, I'm going to join the point up to W1, the length of that vector is the same as if I join it up to W2, no matter where I put Z. So we will end up with a straight line. So if I see one like this, I could expand the whole thing out, of course, and do it via algebra. That would work. Okay. So let's see. Expand the whole thing out. Tidy it up. And there's my line. So I could do that. Or the alternative now is to go, hang on, I recognise this. It's going to be the perpendicular bisector. So I know it's the perpendicular bisector of 1, 1 and minus 2, 1. So I know it'll go through the midpoint, minus half 0. I can find the slope that joins 1, 1 and minus 2, 1. The slope we want, though, will be perpendicular to that. So the slope we want is minus 3 on 2. Point slope formula. And, amazingly, we get the same answer. So I guess it's just how you're thinking at the time when you see the problem. I mean, the algebra in that's not too bad because they were nice numbers. How much work? Probably pretty much the same, really. Not that much more in the second one than the first one. Make sure you read the question. Nowhere in this question did it say, find it. It simply says, sketch it. And that's where knowing it's the perpendicular bisector helps. Because if I didn't know that, then I would have to find it to know what I have to sketch. But if I know it's the perpendicular bisector, okay, I'm going to join it up to 4, and I'm going to join it up to negative 2. Well, halfway between that's 1, perpendicular bisector, there it is. No, yeah, I don't know about you, but I feel really uncomfortable not naming that. So, but it did say sketch. Raise. So here's our definite starting point, in this case the origin, and we're going off at some angle. We can define that to be the argument of z equals whatever that angle is, because every complex number, if I was to join it up to the origin, obviously I would land on that ray, and so it would have the same argument. You'll notice though I've circled the starting point. You cannot find the argument of the origin or the starting point, because if you haven't gone in any direction yet, how do you know which direction you're going to go? So it's not until you start travelling along the ray that you can define what the argument is. So we always circle our starting point of the rays as, say, not included, starting point not included, but then we go off in whatever the direction is. Of course, it doesn't have to be the centre or the origin. We could go anywhere. So if I was to start at some random complex number, omega, and go off, that would be the argument of z minus omega is equal to theta, whatever point we're joining it up to. So now we can ask those regions in the number plane, a good old 2-unit question, but now we can ask it a different way and make it a 4-unit question. So we're going to sketch the modulus of z is less than 1 and the argument of z is in between 0 and pi and 4. Well, the first one, there is our circle. Centre 0, 0, radius 1. Inside or outside? Inside. Yeah. Because look at what it's saying. The distance to the origin, the length of z, is smaller than 1. So I'm closer to the origin than 1. I've got to be inside. Now, argument. Circle the starting point. There's the argument equaling pi and 4. What I should have done... I'll get to that one. But what I was going to say, what I should have done is, once I go past the circle, I should dot that line. That's just a bit hard to do in PowerPoint. But technically it should be dotted, because that part's not included. And the angle is pi and 4. And then argument of 0 would go along the axis. And we're inside, but as was correctly mentioned, when you have a point of intersection where one of those points, one of those boundary lines is not included, we circle the point of intersection. Which questions should we do? I think you should try these ones.